In the last video, we have seen an optimum detection and we derived the optimum threshold for maximum likelihood detection. Now there we constantly introduce the probability of error in binary transmission. In this video, we will make a more rigorous analysis of the probability of error. In all digital communication systems, the most important curve is the probability of error versus the signal to noise ratio, or something called the bit error rate against the signal to noise ratio. So this probability of error or bit error rate that comes as a complementary error function or something called a Q function. Now in this video we will derive the exact expression for the probability of error. So let me start with the presentation. Now the speech is organized into your learning outcome, the derivation of the probability of error and the summary of understanding. So here you will derive the probability of error in binary signaling with the Gaussian noise. So the PDF of the noise is 1 by root 2 pi fn, that is 1 by root 2 pi sigma square e raised to minus n square by 2 sigma square. And if is it given S1, that is the first likelihood function when S1 is transmitted, that is it has a mean of A1 because S1 is transmitted and noise n has 0 mean. So it is if z given S1, the likelihood function, that is 1 by root 2 pi sigma no square e raised to minus z minus A1 whole square by 2 sigma no square. And the second likelihood function, if z given S2, that is 1 by root 2 pi sigma no square e raised to minus x minus A2 whole square, z minus A2 whole square by 2 sigma no square, where A2 is the mean of S2t. Now these two likelihood functions are here. This is f z given S2 with a mean A2, and this is a Gaussian function here, and this is a second likelihood function f z given S1 that has a mean of A1. Now in the last class we have derived that the optimum threshold lambda 0 is midway between A1 and A2, that is A1 plus A2 by 2. This is my threshold. So if my receiver detects Z below this lambda 0, then I make the decision H2, that is S2 is transmitted. If I get an Z value greater than this lambda 0, then I make the decision H1, that is S1 is transmitted. Now, when do I have an error? When I transmit S2t with a mean A2 and some noise is added to that, and some extreme amount of noise is added to that, and it crosses this threshold lambda 0. Now my receiver sees my Z somewhere here, and it makes a decision H1, that is S1 is transmitted. Now there is another case when I transmit S1t, or I transmit S1t here with a mean say A1, and some noise is added to this. It gets subtracted here, and I get my receiver sees my Z value, that is a sampled value at my receiver, say somewhere here. And this region is now it is below lambda 0. Now it makes a decision H2, that S2 is transmitted, but originally S1 was transmitted. Now, what is a probability of error? That is the PH2 given S1, that is the area under the curve FZ given S1 from say minus infinity to infinity, minus infinity to say lambda 0. Originally, S1 S2 was transmitted, but probability H2 S1 was transmitted. So it is PH2 given S1, that is probability of error, that is the area under the curve in the blue region, that is here, from minus infinity to lambda 0. Okay, minus infinity to lambda 0, that is the area under this blue region. Or it is the area under this orange region, that is probability of H1 given S2. That is the area under the curve Fz given S2 from lambda 0 to infinity, that is the area under this orange region. So generally these two are the same. Earlier PH2 given S1, that is the same as PH1 given S2. Earlier we established that PS1 and PS2 are equal and half, that is equal to half. Here we make this statement that PH2 given S1, that is equal to PH1 given S2. So what is the probability of error? Earlier we saw that is PH1 given S2 plus PH2 given S1 into 0.5. So since these two are equal, that half is removed. So probability of error is PH2 given S1, that is equal to PH1 given S2. So one of this I can take. Let us compute the area from lambda 0 to infinity of under this curve f z given S2. So it is lambda 0 to infinity 1 by root 2 pi sigma no square e raised to minus z minus a2 whole square by 2 sigma no square. This is my f z given S2. Now let me make some simple substitution. Say, let this z minus a2 by sigma a naught is y. So dz is sigma a naught dy, sigma a naught dy. And this lower limit lambda 0 becomes the lower limit becomes when integration goes in y, it becomes lambda 0 minus a2 by sigma a naught, where this lambda 0 is nothing but a1 plus a2 by 2, so that this lambda 0 is a1 plus a2 by 2, so it becomes a1 minus a2 by 2 sigma a naught, a1 minus a2 by 2 sigma a naught. So the probability of error is 1 by root 2 pi sigma a naught square from a1 minus a2 by 2 sigma a naught to infinity e raised to minus y square by 2 sigma a naught into dz. dz we established that it is sigma a naught into dy, sigma a naught into dy. So the sigma a naught is cancelled by the sigma a naught, so it is 1 by root 2 pi some a1 minus a2 by 2 sigma a naught to infinity e raised to minus y square by 2 sigma square dy. Now this 1 by root 2 pi x to infinity e raised to minus y square by 2 is nothing but my qx, that's called a q function. Okay, 1 by root 2 pi x to infinity e raised to minus y square by 2, it is q of x, this is a q function. And the complementary, there's a complementary q function of q complement x or q minus x, that is 1 by root 2 pi minus infinity to x e raised to minus y square by 2. These q functions are all probability values because these are the integral of a Gaussian PDF. Now the q function is related to the complementary error function. Another function is called the complementary error function. Q of x, that is half of error function complement x by root 2. Half of error function complement x by root 2. So qx is half error function complement x by root 2. And this is a plot of a q function from 0 to 3 for x from 0 to 3. The maximum value here at 0, the maximum value is 0.5. That is at 0, the value is 0.5. It comes here. So it can be from 1 to 0 because this q function is actually a probability value. So the probability of error, that is q of a1 minus a2 by 2 sigma a naught, because it is this y is nothing but we have here y is my z a1 minus z minus a2 by sigma a naught. So whatever is coming here, this x is a1 minus a2 by 2 in sigma a naught. So it becomes q of a1 minus a2 by 2 sigma a naught. So what is a1 minus a2? That is the difference in mean of the two signals s1 and s2. Let us mark with c d. a1 minus a2 is d, so it becomes qd by 2 sigma a naught. It becomes half of error function complement d by 2 root 2 sigma a naught by the earlier relation. Okay, qx is half error function complement x by root 2. So it is half error function complement d by 2 root 2 a naught. And we know that the sigma a naught is an additive white Gaussian noise, and sigma n0 square, it is n naught by 2, or sigma n naught is root of n naught by 2. The sigma n naught is root n naught by 2. So this root 2 is cancelled. It becomes half error function complement d by 2 sigma n naught. This d square is actually the signal power, or the difference between this signals. This signal power, and this is my noise power. So basically this probability of error is a q function of the signal to noise ratio. So we will be plotting this variation, that is the probability of error or bit error rate against the signal to noise ratio. So essentially they become as a q function or a complementary error function. So when I come to the end of this presentation, here in this video you derive the probability of error in binary signaling with the Gaussian noise. And that is the end of this presentation. I thank you.